Welcome back to this quick introduction to number theory. So what we're going to do today is continue with our discussion of divisibility. And in the previous video, we had seen what the definition of divisibility is, and also the definition of prime and the fundamental theorem of arithmetic. And we used all of that to come up with some like very basic ways of computing greatest common divisors. But what we're going to see today is that even more than like 2,000 years ago, Euclid already came up with an algorithm that is extremely fast, and it's much better than what we had seen before. So what we're going to do now is just through an example, I'm going to show you how to do Euclid's algorithm to find the GCD of 60 and 105. So what you do to do Euclid's algorithm is repeated long divisions, so divisions with quotient and remainder. So I start with the largest number and divide by the smaller number. 60 goes into 105 one time with a remainder of 45. So that's my first long division. And now what I'm going to do is take my quotient and my remainder here, or my the number I was dividing by and the remainder, and then I'm going to do a long division using those two numbers. So I'm going to do long division of 60 by 45, and and then do a long division. That also goes once into 60, and the remainder is 15. Okay, so now do the same thing. Take that number, do long division, take that number, do long division of 45 by 15, and now 15 times 3 is 45, so I get a remainder of 0. Then stop, and the GCD is going to be right here. Why is that so? Why is the GCD there? Well, the GCD is there because what we saw last time was a property. So let me right here recall that if A divides B and A divides C, then A divides B plus C. And in here, if you write here that 45 is 105 minus 60, then what that means is that if you have a divisor, we're trying to find divisors, common divisors of 60 and 105. So if you have a common divisor of 105 and 60, by this equation, if it divides 105 and it divides 60, it has to divide 45. So a common divisor of the two of them would divide the third. And now, well, suppose it divides this, then divides this. Then it divides 60 and 45, so it divides these two, so it has to divide 15. But this last equation with a 0 here tells me that 15, in fact, divides 45. And if 15 divides 45, then it also divides 60. And if it divides 60, since it divides 45 and 60, it also divides 105. So what we've concluded is that a common divisor of 105 and 60 would divide 15, but 15 is a common divisor of 15 and 60, so that has to be the GCD. So let me explain that again. If D divided 105 and D divides 60, so it's a common divisor, and we have this equation between 105 and 60, then D would divide 45. But also, if D divides 60 and D divides 45, and 15 is 60 minus 45, then D divides 15. But the fact that 45 is 15 times 3 implies that 15 does divide 45, and then from the equations above, 15 actually divides 60 and 15 divides 105. So between this and that, so we get here that any common divisor divides 15, but 15 is a common divisor, so that has to be the largest common divisor. Okay, so what we get out of all of this is that the GCD of 60 and 105 has to be 15. thanks to Euclid's algorithm, which is again nothing more than repeated long divisions. Let me show you another example of this. So for example, the GCD, let's compute the GCD of 322 and 245. Okay, that's not so clear what that GCD would be. So let's do the algorithm. We do repeated long division. That is 1 plus 77. Then 245 is 77 times 3 plus 14. Then take 77 and divide it by 14. That's 14 times 5 plus 7. And 14 is 7 times 2 plus 0. So I reached a 0, and here is the GCD. So the GCD of 322 and 245 is 7 by Euclid's algorithm. And again, you can see that a common divisor of these two would divide this, would divide this, would divide this. So a common divisor has to divide 7, and 7 divides all these numbers also, so 7 has to be the GCD. So voila. Okay, so now I promised that this was actually very efficient. So let me just give you, I'm not going to prove this, and I'm not going to be too concerned about the efficiency of algorithms, or I'm not going to prove theorems about their efficiency, but what is happening in this algorithm is just long division. So the question about the simplicity of this algorithm is how many long divisions happen, and it turns out that one can show that the division step is executed in Euclid's the Euclid algorithm of A and B is so here A is assumed to be bigger than B, at most 2 times the log of 2 of B plus 2 times. And that is really good. The logarithm is a function that grows very slowly, so this will be a very small number of steps in general because of the growth of the logarithm. Okay. Now, one more thing we can do with Euclid's algorithm is solve Bezout's identity. So why are we interested in this? It will become clear when we talk about congruences, and in particular when we talk about multiplicative inverses of congruences. But for now, let me show you what that means. So what we're going to do is find a solution of the equation 1 is 7x plus 5y with integers x and y. This is what's called Bezout's identity. Where here 1 is the GCD of 7 and 5. So the 1 that appears here, that 1 is the GCD of 7 and 5. So we're going to find a solution to that equation using Euclid's algorithm and then sort of reversing Euclid's algorithm. So we start with Euclid's algorithm. First, use Euclid's. 7 is 5 times 1 plus 2. 5 is 2 times 2 plus 1. And then 2 is 1 times 2 plus 0. So here's the GCD. And then what we do now is we solve for all the remainders, and we're going to use those equations in a moment. So I'm going to write 2 as 7 minus 5, and 1 as 5 minus 2 times 2. Because now I'm going to start with the equation 1 is 5 minus 2 times 2. And then use this equation here to substitute that 2 for 7 minus 5. So 5 minus 2 times 7 minus 5. Now I want to collect 5s and 7s, so I don't want to multiply through 2 times 7 just being 14 and 2 times 5 equals 10. I want to have multiples of 5 and multiples of 7 at the same time. So I'm just going to distribute that 2 and write 2 times 7 plus 2 times 5, and then collect 7s. So this is minus 2 times 7, and collect 5s. 5 and 2 more 5s, that's 3 times 5. And here we go. We have it, because this is telling me that 1 is a linear combination in integers of 7 and 5, which is what I wanted. So the solution is x is minus 2 and y is 3. That's my solution to Bezout's identity. So that we were looking for. Okay. So the upshot is that what this shows, well, we haven't really shown anything, but this works in general, is that Euclid's algorithm, or reversing Euclid's algorithm, like so, can write, with that you can write the GCD of two numbers as a linear combination of integers of those two numbers. Okay, so this is what I did. Write 1, the GCD, as a linear combination of 7 and 5 multiplied by integers. So that's a linear combination in terms of integers. I can write 1. Okay, let me show you another example of this. So I'm going to solve now. So we know that the GCD of 322 and 245 is 7. So the question is, solve Bezout's identity. Bezout's identity, I want to write 7 as a linear combination of 322x and 245y with x and y integers. So I want to be able to write 7 as a linear combination of those numbers. Now that seems difficult, but with Euclid's algorithm is actually not that bad. So we had before our work of Euclid's, that is 245 is 77 times 3 plus 14, and 77 is 14 times 5 plus 7. And then I'm going to use these equations to solve for the remainder. So 7 is 77 minus 14 times 5, and 14 is 245 minus 77 times 3, and 77 is 322 minus 245. Okay. And now I'm going to start working to solve the equation. To solve Bezout's equation, I start with 7 is 77 minus 14 times 5. And now substitute 14 in terms of this 14. So use this equation to substitute 14 there. So this is 77 minus 245 minus 77 times 3. This is a minus and this is a times. Times 5. Now collect 77s and collect 245s. So this is 77, 1, and 3 more 77s. This is 4. No, what am I doing? Let's not rush into it. Let's expand first. 5 times 245, so we don't make a mistake. And then 15 times 77. This is with a plus. And then if we collect the 77s, I get 16 times 77 and 5 times 245. Great. And now I can substitute my 77 in terms of 322 and 345, which are the numbers I want at the end. Okay, so this is 16 times 322 minus 245 minus 5 times 245. That is 16 times 322 minus 16 times 245 minus 5 times 245. And what that, at the end of the day, what I get is that 7 is 16 times 322 minus 16 and 5 is 21, so minus 21 times 245. And that is my solution, because what this says is that 7, let's write it here, 7 is 16 times 322 plus minus 21 times 245. And that is a linear combination of the GCD in terms of integers and the numbers that I started from, 322 and 245. So the solution was that x is 16 and y is minus 21. So that is my solution to this equation. And again, this will be used to find multiplicative inverses later on. But more generally, what this algorithm is doing is finding one solution of Bezout's identity, but in fact, you can find all of them. So let me show you the actual theorem of how to solve Bezout's identity. Is that to suppose that the GCD of A and B is D, then the Bezout equation AX plus BY equals D has an integer solution, which can be found using Euclid's. And moreover, if X naught and Y naught is just one solution that we found, say using Euclid's, then every solution is of the form, so there's an equation for all the solutions, and the equation is x0 and y naught, so that initial solution, and then plus a correction factor and minus a correction factor. For the x, since x goes with a, is b times k divided by the GCD, and since y goes with b, then it's a times k divided by the GCD for some k in the integers. So what this is telling you is, if you find one solution of Bezout's identity, these formulas give you all the solutions of Bezout's identity. So let me give you an example. So for example, we just had that 1 is 3 times 5 minus 2 times 7 was a solution of the Bezout identity for 7 and 5. So 1 is 5x plus 7y has a solution x naught y naught equal 3 minus 2. So that is one solution to that Bezout identity. Then the rest of the solutions are given by that theorem I just stated. The theorem would tell you that x is going to be given by the initial solution plus a correction factor minus a correction factor, and 3 goes with 5, so it's times 7k divided by the GCD, which in this case is 1, and minus 2 goes with 7, so the correction factor is 5 times k divided by 1. So this is 3 plus 7k, and this is minus 2 minus 5k for all k in the integer. So all of those are solutions. So for example, when k is 0, I get 3 comma minus 2. That corresponds to k equals 0. But if I put k equals 1, then I get 10 and minus 7. So is that so? Well, 1 is 5 times 10 minus 7 times 7, that's 50 minus 49, which is 1. So yes, 10 and minus 7 also work. By the way, why does this work? Why do those all work? So let me show you that all of those solutions actually work. So if I plug in, so is this really 1? If I plug in for 5, 3 plus 7k, and I plug in for y minus 2 minus 5k, then what happens? What I get is 15 plus 35k minus 14 minus 35k. So the 35k and the 35k cancel out, and then all I get is 15 minus 14, which is 1. So it works, and that's why it works, because it reduces, those correction factors just cancel out, and it reduces to the solution of Bezoos, which was given by the initial solution that we found using Euclid's algorithm. Okay, so then next, what we're going to do in the next video is talk about congruences and congruence classes.